Hello everyone. Today I will present you 4 novel algorithms for parallel masked sparse matrix multiplication. As we all know, sparse matrix multiplication is a very important linear algebra kernel. It is used across many domains like combinatorial and graph algorithms, including graph BLAS applications, bioinformatics, and data analytics applications. It is computationally and memory very expensive, therefore we need efficient algorithms. It is also very often executed with mask. Some of the examples where we have SPGM followed by masks are between centrality, Markov clustering, trivial counting, and multi-source BFS. If we need only a subset of the output elements, then we can specify those elements as sparse matrix and perform matrix multiplication followed by element-wise multiplication. So in this example, we multiply A and B to get temporary matrix C. Then we provide the needed elements using a separate matrix which we call mask, and perform element-wise multiplication to extract the needed elements. The operation of multiplying temporary matrix and mask is also known as masking. So we have seen on the previous slide how to one way to implement a mask SPGM, that is, we first perform sparse matrix multiplication, and then we perform mask operation, that is element-wise multiplication, as a separate operation. The problem with this approach is that we perform unnecessary arithmetic operations, we perform unnecessary writes to memory, and we have to create a necessary temporary object. In this work, we propose fuse mask matrix multiplication, where we reduce the number of arithmetic operations, we reduce the number of writes to memory, and we don't materialize intermediate result. Therefore, we need less memory to execute the algorithm. Sparse matrices have a lot of different patterns. For example, they have also huge variance in dimension, number of non-zeros, sparsity, and non-zero structure. Therefore, none of the algorithms is going to be best for all inputs. In this work, we propose 4 novel algorithms for mask SPGM. 3 of them, mask plus accumulator, mask hash accumulator, and mask heap, are based on previous Gustafson SPGM algorithms, and mask compressed accumulator is the completely novel algorithm. In addition to these 4 algorithms, we provide variations for complemented mask algorithms. Here I will show you the overview of the algorithm, of the all 4 algorithms. Each row in C is calculated as a linear combination of rows in B that is later masked with a row from mask. So in this example, if you want to multiply matrices A and B and mask them with mask to get final matrix C, we will need a single row from mask, single row from A, and multiple rows from B that are selected using a current row from A. After we create all these operations, we will use a data structure called Accumulator to generate the final output row C. Now I will show you the first of our algorithms, which is called mask sparse accumulator. It uses dense arrays to accumulate values. It uses 2 different arrays. First one is a states array, and each state can have 3 values: do not compute, compute, or partially computed, and values array, which contains cumulative values. Initially, all states are set to do not compute, and all values have undefined. All values in a value array have undefined values. Then we take a current row from mask, and we take for each non-zero in mask's row, we take corresponding elements in states array, and we change state from do not compute to compute. Then we take a row from B, and for each non-zero in a current row from B, we check the corresponding state values for each non-zero, and if the values do not compute, we ignore that element. In this case, we will ignore first element and the last element from B1. Then from B3, we again ignore the first element, but we compute for the second last element, and after we compute it, we store the value to the values array. Then for B4, again, we ignore the elements with index 2, but elements with index 4 and 6, we compute them because states array contains a value compute or partially computed. Finally, for B7, element with index 4 won't be computed, but element with index 6 will be computed. And in the end, we use again a row from mask. For each element in a mask, we look at the corresponding element in the states array, and if the value is partially computed, then we remove the value from the values array and store it into output rows from C. In addition to mask sparse accumulator, we have 3 other algorithms. First one of them is hash accumulator. It is very similar to mask sparse accumulator, but it uses hash table instead of dense arrays, and this algorithm has better cache behavior if dense arrays do not fit in cache. Then we have heap accumulator. Heap accumulator uses a heap for merging AIK, BKJ products, and this algorithm is very similar to multi-way merge. And finally, we have mask compressed accumulator. It is based on the fact that accumulator cannot have more elements in a mask. And the algorithm first finds intersection between each row in B and mask. This is the complexity summary for each of the algorithms. We can see that the time complexity from MSA and hash is the same. However, MSA has much larger memory footprint. And then for heap algorithm, we see additional logarithmic factor in time complexity, but we also see very low accumulator memory footprint. And similar thing if we have MCA, where you have additional multiplier factor in time complexity, but we have a low memory footprint. To summarize, MSA works is very fast if the accumulator fits in cache. Hash has additional cost of hashing and probing, but it usually fits in cache. Heap has additional logarithmic factor and small memory footprint, and MCA works very well for small masks and usually fits in cache. Another important aspect for mask SPGEM accumulator is how to calculate the size of the output, and there are 2 approaches. First one is we calculate the exact size of the output. We can do this by performing symbolic computation to find out the size, and after performing symbolic computation, then we perform numeric computation. And this set of algorithms are also known as two-phased algorithms. In contrast to two-phased algorithms, we have algorithms that estimate the upper bound for the matrix size, and then after calculating the values, then we just copy data to the array of appropriate size. And since these algorithms have only numeric phase, these algorithms are also known as one-phased algorithms. In our implementations, we support both one-phased and two-phased algorithms. We evaluate all algorithms on query, on Haswell nodes and KNL nodes. Haswell nodes have two 16-core CPUs that run 2.3 GHz, and they have 128 GB of RAM, and KNL has 68 cores and 96 GB of RAM. For inputs, we used both real-world matrices and synthetic matrices. For real-world matrices, we picked 26 matrices from previous work, and for synthetic matrices, we use RMAT and ER matrices. The synthetic graphs are usually preferred for control experiments in which we vary degree or size of the graphs and investigate their effects on various performance metrics. For benchmarks, we picked 3 applications. First one is triangle counting. For triangle counting, we calculate the total number of triangles in a graph, and this application uses only one mask SPGEM operation that is later followed by reduce. For second application, we use K-truss, which is a bit more complicated than triangle counting. It finds the edges that are supported by at least k-2 other edges, and it uses mask SPGEM in an iterative manner. And finally, we have betweenness centrality. Betweenness centrality measures how central is a node in the graph, and it uses plain and complemented mask SPGEM algorithm in an iterative manner. Before showing results for the applications, we'll first see the mini benchmark. We generate multiple matrices using ER inputs. We vary size. Each of the plots show different input size. We vary the degree of the mask and degree of A and B. That is, we vary the average number of non-zeros in each row of M and each row of A and B. And here we can see that inner product, the mark with red, is the best algorithm when the mask filters a lot of non-zeros from the output. We can see the heap is the best one in the opposite case, when the mask has a lot of non-zeros. And in between we can see that MSA and hash have the best performance. And MSA is very good for small sizes, of small dimensions, which is expected, because in that case the dense arrays fit in cache. However, as we increase the dimension, the dense arrays do not fit in cache anymore, so hash algorithm has much better performance. I will now show you the results for triangle counting, and to show you the results I will use the performance profiles. For point x, y represents the fraction of test cases that are within x factor of the best obtained result. For example, for this point here, it means that MSA 1p is in 80% of cases it's within factor of 1.2x. And for example, this point here tells us that MSA is the best algorithm that is within 1.x factor for 65% of the test cases. Also, on this graph we can see that one-phase algorithms are almost always better than two-phase algorithms, and that MSA is the best algorithm in 65% of cases. However, we can also notice that MC algorithm has the best worst-case performance. Also, heap algorithms are the slowest, and therefore they will be excluded from the further analysis in this presentation. Now we compare our algorithms with GrabLAS, also using performance profiles. We can see that our algorithms outperform GrabLAS in almost all cases on Haswell, and we can also see the performance on KNL is very similar to performance on Haswell. This plot shows student scaling for triangle counting. For the matrix we use RMAT generated matrix with degree 16 and scale 20, which means that on average each row has 16 non-zeros, and we have 2 power by 20 rows in the matrix. All algorithms on Haswell scale well up to all 32 cores, and we can see similar trends on KNL, where all algorithms scale pretty well up to all 68 cores. The next application that we use for evaluation is K-truss, and our algorithms for K-truss outperform GrabLAS in almost all cases. We can see that MSA is the best one on Haswell, whereas inner product is the best one on KNL. Now we evaluated K-truss using synthetic RMAT matrices, where we scale where x-axis shows scaling with size, with input size. And here we can see that MSA is the best algorithm on Haswell, which is closely followed by Sparse dot and inner product. And on KNL, Sparse dot is the best one, and it is closely followed by our inner product implementation. For the last application that we implemented is between centrality, and we can again see that one-phased algorithms are faster than two-phased algorithms, and we can also see that the MSA is clearly the winner in this case. It is the fastest algorithm for all matrices that we use as inputs. For between centrality, we also use the RMAT matrices. And again, as MSA is the fastest algorithm, we can see that for all inputs, MSA has the best performance on both KNL and Haswell. In conclusion, we presented 4 novel algorithms for performing mask SPGEM. We also use extensive set of experiments. We use a large set of real matrices and 2 types of synthetic matrices. We use 2 architectures, Haswell and KNL, and 3 real-world benchmarks, triangle counting, K-truss, and between centrality. And we've shown that our methods significantly outperform Sparse GrabLAS. For future work, we want to implement hybrid algorithms because we have noticed that no algorithm is best in all scenarios. Therefore, we want to develop a hybrid algorithm which will use different algorithm for each row. Additionally, we want to implement a GPU and distributed memory implementations. And finally, we want to design an algorithm for general fusion. That is, we want to fuse arbitrary sequence of sparse kernels like mass multiplication, element-wise additional multiplication, assignment, extraction, and so on. Thank you.